Hello everyone. Today we start discussing chapter 3, which is about sequence and theory. The first section, 3.1, is about sequences and their limits. Let's start with a definition. A sequence is essentially just a function from the set of all natural numbers to the set of real numbers. Remember, we spent the whole chapter 2 discussing this set of real numbers. If we noted that a sequence is often is denoted by the following notation. X is denoting a sequence of elements called Xn. So here the sequence exactly a list of numbers from x1, x2, and so on. X1 essentially is the value of the function at input 1, x2 is the value of the function at input 2, and so on. Here are a few examples. For example, you have sequence of 1, 1, 1. Each element in this sequence is equal to 1. Then the general formula for this sequence is that xn is equal to 1. Now, another sequence is given as follows. X here is a sequence of 1 over 2n with n here a natural number, an element in the set of all natural numbers, capital N. Then xn in this case is equal to 1 over 2n. That is, the sequence is basically the list of numbers 1/2, 1/4, 1/6, and so on. Also, a sequence can be given in a recursive manner. For example, you have the following sequence. F1 equal to 1, F2 equal to 1. Then there is the general formula, general recursive formula. F of n plus 1 gonna be equal to the summation of fn plus fn minus 1. That is, in order to compute the next element in this sequence, we take the sum of the previous two elements. For example, f3 is going to be equal to f1 plus f2, which equal to 1 plus 1 equal to 2. f4 similarly is equal to f2 plus f3, which is equal to 1 plus 2, which is equal to 3. This sequence is actually a very famous sequence by the name Fibonacci. So now you have a general understanding of what a sequence is. Let's talk about the limit of a sequence. Here is the definition. A sequence is said to converge to some number, some real number x in the set of all real numbers, capital R. Then x equals a limit of this sequence. If for every epsilon greater than 0, there exists a natural number k, probably depending on epsilon, such that for all natural number n greater than or equal to k, then xn minus x in absolute value must be smaller than or equal to epsilon. That is, eventually every element in this sequence will be within epsilon distance from this number x for any epsilon greater than 0. If such situation happens, then x equals the limit of the sequence. And when the limit exists, the sequence is said to be convergent. And if such a number doesn't exist, then the sequence is said to be divergent. Equivalently, the definition can be interpreted as follows. The sequence xn converges to some number x, even only for each epsilon greater than 0, the epsilon neighborhood of x, v epsilon of x, contains all elements of the sequence except for finally many terms. So let's visualize the sequence as a list of numbers on the real line. Then for any number epsilon, you can construct an epsilon neighborhood around this point x. So here, this is exactly the epsilon neighborhood here around this point x. X is the limit if for any number epsilon, this small neighborhood actually contains most elements, almost all elements in this sequence, except for finally many terms. And remember, the key word here is that this is true for any epsilon greater than 0. That is, you can choose epsilon as small as you wish. The neighborhood here as small as you wish. It still contains almost all elements of the sequence except for finally many terms. Here are a few examples. Example 1. The limit of the sequence 1 over n equal to 0. So in this case, you have xn here equal 1 over n. Now, why this is true? In order to see this, let's pick any number epsilon greater than 0. Then obviously, 1 over epsilon greater than 0. We're going to use a very important property we learned in the previous chapter. That is the Archimedean property. And according to this Archimedean property, there exists some natural numbers k, possibly depending on epsilon, such that 1 over k is smaller than epsilon. If n greater than equal to k, then obviously we have that 1 over n is smaller than equal to 1 over k, and this is smaller than epsilon. That is, the absolute value of 1 over n minus 0, which equals 1 over n, is smaller than epsilon. But this is exactly the definition of the limit of 1 over n equal to epsilon. And this is the end of the proof. So you see that the proof is actually just list consequences of the definition, and also an application of the Archimedean property that we learned in the previous chapter. Here is another example, the limit of the difference between the square root of n plus 1 minus square root of n is also equal to 0. So in this case, xn here equal to square root of n plus 1 minus the square root of n. The proof here is similar to the previous one, so we're gonna skip it. You can read for details in the lecture note. Now, a very important theorem for limits is about the uniqueness of limits. That is, a sequence can have at most one limit only. That's why a limit equals the limit. Because the sequence can have at most one limit, so as long as we find a limit of this sequence, it is exactly the limit of the sequence. Another important concept related to sequences and limits is about tails of sequences. Here is the definition. A sequence x equal to xn and we consider some natural number m, then the m tail of this sequence x is a sequence defined as capital X of m here equal to small letter x m plus n for any natural number n. That is, this is the sequence of xm plus 1, xm plus 2, and so on. Basically, in order to obtain the m tails of a sequence, we just delete the first m elements in the sequence, and the rest equal the tail of that sequence, the m tail of that sequence. An important theorem is that the limit of a sequence is exactly equal to the limit for any tail of that sequence. Limit of the sequence x equal to the limit of the sequence capital X m for any natural number m. So what does this theorem about? This theorem basically says that the limit describes the behavior of infinity. If you remove finitely many terms from a sequence, it doesn't change the limit behavior. That's why the limit of sequence is equal to the limit of any m tail of that sequence. We have another theorem which is useful to determine the limit of the sequence. It says the following. Let Xn be a sequence An be another sequence such that each element An is greater than 0 and the limit of An is equal to 0 when n approaches infinity. Suppose that there exists some number c greater than 0 and some natural number m such that the absolute value of the difference between x and x is smaller than equal to c multiplied with an for all natural numbers and bigger than equal to m, then the limit of xn is equal to x. Basically, the content of this theorem is that the epsilon neighborhood in the definition of the limit is replaced by a comparison with a positive sequence converging to 0. Okay. And here is an example how that theorem is applicable in practice. Let's consider the sequence xn equal to 1 over 1 plus na for some number a greater than 0. We would like to determine the limit when n approach infinity of xn. How do we do that? We consider the difference of 1 over 1 plus na and 0. This is exactly equal to 1 divided by 1 plus na, and this is smaller than or equal to 1 over the absolute value of na, which equal to 1 over the absolute value of a times 1 over the absolute value of n. But a and n are positive numbers, so the absolute value of a is equal to itself, the absolute value of n equal to itself. That's why this equal to 1 over a times 1 over n. We know that the limit of 1 over n equal to 0 when n approach infinity by the previous example. That's why applying the theorem above for c equal to 1 over a n equal to 1 over n, then we can conclude that the limit of this sequence 1 over 1 plus na equal to 0. Basically, we show that the difference between this sequence and 0 is smaller than a positive sequence of converging to 0. That's why the limit of this sequence is equal to 0.